Okay. Nice. All right. So today, okay. Today we'll talk about multitask and multilingual learning. Um, yeah. So just to recap, right? Neural networks are just feature extractors, and what this means that given a sentence or a collection of other things or whatever, speech, images, whatever, all they do is eventually create a vector representation or a representation that's created by several different vectors, and these are used for the downstream tasks. Now, the idea behind multitask or multilingual learning in general is that these representations can be used for several of these multiple tasks. And of course, the prime example in our case, when it comes to language, is just word embeddings, right? Because they're just a representation of language that you can use for any other downstream task, from machine translation to tagging to whatever. When it comes to the different types of learning, multitask is just a very general term, and we'll talk about how other things that are labeled differently are practically just an instance of multitask learning. So transfer learning, right? Can someone give me, well, I just opened it up, but transfer learning is just one type of multitask learning, right? But the only difference is that we only care about one of the tasks out of all the set of the tasks that we have trained in. Can someone give me an example of transfer learning? Like anything, something. No? Like how many of you are using BERT in your projects? Well, you should be able to give me an example of transfer learning, just saying. Okay, then even domain adaptation, which is a very specific type of transfer learning, in this case we have basically the same task, right? When you're doing domain adaptation for machine translation, the task is machine translation. But you want to be able to handle different inputs that come from different distributions. But that can also be viewed as an instance of transfer learning, right? The way that a task is defined can be very narrow. You can have the task of translating English poetry into French poetry, right? And you can have a different task, which is translating English news headlines into French news headlines. And if you view them as different tasks, then basically this different domain adaptation setting is also a multitask setting. So when should you multitask? Did any of you answer like always in the quiz? Because that's not exactly correct, right? I mean, there's no guarantee exactly that, if you just multitask, then suddenly everything will get better. So, however, there exists so many tasks in NLP, and all of them deal with language. So they're at least related with respect to at least their inputs or their outputs, depending on the tasks. And all the different tasks that we have talked throughout this class, they require different varieties of data. So in one case, you might only have natural occurring text, right? And you might be training with tasks that are basically do not require any other labels. Like when you do language modeling, all you do is you use the text to try to predict the next word, and you don't need any other additional labels. You can also use other natural occurring data as labels. So if you're doing machine translation, then people have been creating parallel corpora even involuntarily, and so that's another signal that you can get from naturally occurring data. Or you might be using hard label data, which includes basically most of the analysis tasks, right? Like when you do part of speech tagging, these labels were created by linguists or annotations that were trained, and basically almost all of those tasks require this type of data. And then there's the whole other thing that, all of these tasks, they are also like applicable to many, many languages. And they could be, by the extension that we talked before, that they also could be viewed as different tasks to different domains, right? So a very simple example is that if you're doing syntactic parsing on text from news articles, right? Which is usually well-crafted and proper sentences. And if you do parsing on speech, where you have like hesitations, you have incomplete sentences, you have like much longer segments that could be a bunch of different sentences. That like the output distributions look very, very different. So across domains, across languages, and across like the different varieties of data that your models will be operating on, then you have all these different things to choose from. So I'll just give you the two like rule of thumb options on when to use multitask learning. And the first one is to use multitask learning to increase the size of the data that your model has learned. So if you have two tasks and one of them has much, much fewer data than would be potentially enough to even train like a neural net, right? We only have, let's say we're doing machine translation in this case, and we have a bunch of medical text in English and just 10,000 translations of 10,000 sentences from this medical text in French. These could provide some signal, but they wouldn't be necessarily good enough or enough in order to train a really good machine translation system between English and French. So what if you have a general domain? So you go from a general domain like web text and like all of the other parallel data that you have between English and French, and you use that in order to go into a more specific domain. In another case, you might have like lots of data in one language, but just a few data in a low resource language. And you could try to exploit similarities, not even necessarily similarities in languages, but just maybe similarities in the annotation scheme of the language, of the downstream task that you care about. And notice here that in this case, these high resource language and the low resource language could be either provided as a source. So if we're doing machine translation, right, again, and we have a ton of English-German data, but we only have just a few Telugu German data, right? You can train on both of them and do basically multitask learning, where the two tasks, the first task is English to German translation, the other is Telugu to German translation, and still benefit because the output is the same. Or it could be the opposite. You could have sharing things in the source. So in this case, we want to translate from German into Telugu, but we only have just a few data. So we use the ton of German to English data that we have to learn proper representations for the same source, the German, that we then use for our German to Telugu system. Yeah, or you might want in general to go, if you have a task that for which you only have a few labeled examples, so like independency parsing and syntactic parsing, in all of those cases, we rarely have a ton of data to train our systems on. So what if we started with the lots of plain text that we have that presumably follows the same distribution of the labeled text that we have because they are the same language, and then we use that to learn our representations and then use them into the downstream label task. So that was the first rule of thumb. Like if you don't have enough data to train what you deem a good system, then potentially you could use multitask learning to use more. Another one is that the tasks have to be somehow related or similar. But these are like kind of like fuzzy notions of when are two tasks necessarily related. One could say that when it comes to language, since all of our data either operates on language or produces language, they're all related, right? In general, what you want is you want the two tasks to basically help. The one task you want, well, it's kind of like to both ways, but you want the two tasks to help each other generalize better, right? So you want the two tasks to basically use at least a subset of the same features to make their decisions, right? So when you all use the pre-trained BERT that was trained on a masked language modeling task, why are these contextualized embedding useful when you're doing sentiment analysis, right? And the answer to why they are useful is that basically the two tasks, even though they're so like they seem so different, they basically learn very similar features in order to produce their output classification. Yeah, and there's tons of examples of related tasks that have been used. One very nice is that seems like two different, and then one is like summarization from the NLP, summarization of big articles into concise short paragraphs, and the other task is predicting the eye gaze of humans. Right? So when you look at long chunks of text, you don't focus with the same, not weight, but with the same, you know what I mean, with the same weight on every single word or every single sentence. So if you can ask the model to learn to focus just like a human does, or like which is basically the equivalent of predicting where the human would focus, right? Then maybe you can learn better features for summarization. Yeah. So we'll go through a bunch of methods for doing multitask learning, and in the standard version, what we care about is we have like a shared encoder that basically learns representations that would do well on multiple tasks at once. So if you want to do both translation and tagging, you would just train your model using a shared encoder. And in general, this is as simple as, is anyone aware of any data set that has both source and tags and translations? And I mean, they might exist, but the point is that these are like quite hard to find. So, however, you have a bunch of data that are parallel data that you can use for translation, and you have other data that are the same source language with their tags. So what you can do is alternate between the two tasks and pick mini batches, so that when you pick a translation mini batch, you do a forward through the encoder and the translation decoder and propagate back. Or when you have picked a tagging mini batch, you use the tagging decoder, but propagate through the same encoder, right? So the encoder learns representations that are useful for both of these tasks. And you can do that with as many tasks as you want. And of course, there's many examples that do this in the literature. Another version is pre-training, where we, instead of alternating between the two tasks, we first train on the first task, and then we fine-tune or do our training on the second task. And in this case, clearly the assumption is that we only care about the second task, right? And the way that you do that is that you train your model in the first task, and then you decide which components you will want to keep in order to initialize your the second task's model with them. Now the problem here, and again, like the prime example is just reusing word embeddings to initialize your lookup parameters in any of your guys' models. There's also work on not just pre-training in order to learn word embeddings, but also even just using full sentence representation, like a single vector for a sentence that you could then use for downstream tasks. Right. Now, it's very common to use different types of encoders, and one question is, what should you use, or which task should you pre-train your encoder on, right? And typically in these cases, what we want to do is basically learn really good representations by utilizing the vast amounts of monolingual data that we have, right? So one option is to, so you don't have any labels for that first, for the first like task that you're pre-training on. So typically people have used like just language models where the task is predicting the next word, or translation models, because also there happen to be big data sets that are parallel, not, at least in some languages. And then Elmo came out and they were using bidirectional language models. And the improvements here is that basically you learn those contextualized representations, right, that we talked like a month or two ago. And finally with BERT, you have different objective, which is uses the transformer, and you have the masked language model. Note that also BERT is not just trained on this masked language modeling objective, right? BERT is also by default trained on a multitask objective where the one task is predicting the masked words, the other one is doing classification over pairs of sentences. But then you just take the representations or the weights and you transfer them into your fine-tuning on the final task that you care about, and you do great. One thing that you need to be kind of careful about is pre-training basically relies on the fact that you have learned really, really good representations from your vast monolingual data, and you don't want, when you fine-tune in the downstream task, you do not want to like move too far away from them, right? So one thing that you could do is just fix them and not update them at all. However, there are reasons why you might want to actually train them, right? There might be a specific domain that your second task is more focused on or something like that. So one option is generally to use some form of regularization in order to make sure that our weights do not move too far from the initialized ones. And one way to do implicit regularization is early stopping, right? So I'm pretty sure all of you know what that is. But basically, this is a form of implicit regularization because you make sure that you don't overfit your data, and presumably not overfitting means you do not update those parameters too much. Or you could do explicit regularization, where you can have an additional component in your loss function and penalize large differences from the initial values, right? And this is how this language would, this loss function on the right would look like. You still have your normal P of the outputs that you want, given X, from the original parameters, from the parameters of your model, given the parameters of your model, but you also penalize the difference of those parameters that you learned from the initialized ones. And again, presumably, this will keep the model from updating the parameters too much, or basically the model would only update the ones that are absolutely necessary in order to, for example, adapt into this new domain or these specific tasks. And finally, another thing that you can do is just use simply dropout, which is another implicit form of regularization. And the reason that this fits in here too is because if you think about it, if you initialize a bunch of parameters with the pre-trained models parameters, and then you use them, but then during training you do dropout on them, right? The parameters that you masked with dropout don't get updated, right? So that's keeping at least half of them close to the original ones, or if you use dropout of 0.5, half of them close to the original ones. Right. Another thing that you might want to do, and it could potentially work better, is to only adapt part of the parameters, right? So in the case, for example, of domain adaptation for machine translation, right? Do you need to retrain a full transformer model, like 8 by 8 layers and all these parameters, or do you maybe, just need to just initialize your domain-specific model and just update like the final softmax or the source embeddings or a smaller part of your model which would allow you to basically train much, much faster, right? So in this case, in this work, Barone and others examine the best parameters to adapt in a multilingual neural machine translation setting. So basically, they had a good pre-trained model on, I don't remember the language, but let's say it was French to English, right? And they wanted to adapt it to do German to English. So without without training, without retraining, right? So if you just use the French to English model to do translation of German, the dev blue is just 0, right? Okay, that makes sense. If you only retrain the source embeddings, then they were able to, get from 0 to 7, and all the other parameters are the same. Or you could retrain the source embeddings, which ended up being super important. You cannot not update the source embeddings. Depending on which components they updated, you get different results. So you can see, for example, that in this case, the target attention was the most important one compared to the others, presumably because the languages were not French and German and English, and there was, although French and German would have that distinction, you'd need different attentions because they have different word orders, at least in some cases. Yeah, there's another, I wanted to show you, or maybe I have it later. If I don't, I'll just show it later. So another way that in general you can do multitask learning, instead of doing this hard sharing of parameters like we saw in the very beginning, or by this transfer of parameters with initializing, is you can do soft parameter tying. And what this means is basically you tie the parameters, so instead of actually sharing them, you have different parameters that you force to be similar or close to each other. So in this work, the parameters are regularized to be closer to each other, but they are not exactly the same. So this soft tying allows basically, before when we talked about the regularization of the initialization, this is the equivalent of when you train the two models at once, right? In the pre-training, where you regularize the parameters to be not different from the initial case, you can think of like the left model being fixed and pre-trained, and then you're training the right model with the regularization, or you can train both of them at the same time and have this soft tying of the parameters, right? Okay. The next thing that I want to talk about is domain adaptation. Let me just find the other thing that I want to show you. It was from a paper that, one second. I want to show you an image from, it's taken from a, from a very recent paper by Peters and others, where they took basically Elmo and Bert that are now widely used for several downstream tasks, and they wanted to see if it's better to just freeze the parameters, which they generally denote with the snow emoji, or to actually update them for your downstream tasks. And they found that whether you use Elmo or Bert and you decide to freeze them, then ideally you have many additional parameters that will learn to manipulate the frozen contextual embeddings in a way appropriate for that task. Or if you want to actually update those initialized parameters, then you don't need that many additional task parameters, but you need to be careful with your model's hyperparameters so that you don't have, for example, a super high learning rate that would move all the initialized parameters too far away from their initialization. Yeah, and they also, it's interesting that with Elmo they found that for sentence pair classification tasks, it's better to just use to freeze the contextualized embedding, but with Bert it was the opposite. So I just wanted to show you this. Right.
I also think this table is an interesting example of natural language processing. So you could answer a question with respect to that table should I pre-train or should I freeze the parameters or fine-tune the parameters of Elmo when I'm doing a sentence pair task? Then I think you solved much of natural language processing. Number one, you need to understand the like snowflake emoji means freezing the parameters.
Yeah, sorry.
Yeah,
but yeah,
it's
so,
just a joke. But
yeah. All right. Yeah, so domain adaptation is, again, as I said before, it's just another, in this view, it's just another way of, a very specific instance of multitask learning, where you have the same task, but the incoming data can come from very different distributions. So, again, for the machine translation task, you might have news text or medical text or just spoken language, like I said before, and even though they all might be English or Telugu or whatever, these different domains will have very different distributions in terms of the actual language that is used. And typically what you have is, you train on a general domain, which general domain is not exactly a thing. A general domain is just a domain. It's data from a general domain are data that include data from multiple domains. Okay. Sorry if that was confusing, but you know what I mean. And yeah, and the notion is that some domains are so different from others, like say medical text, that you might want to fine-tune and have a specialized model for that particular domain. So you can do this both in a supervised way, if you have labels for the domain that you're interested in, or even in an unsupervised way. So in supervised adaptation, you do have data in the target domain, and the simplest thing to do is just pre-train on all the data that you have, and then just do fine-tuning, like continued training, quite possibly with carefully selected small learning rates in order to, again, to not deviate too much from your initialized parameters into training to your domain-specific data. Or you could also just use learn domain-specific features or a domain-specific network. So you could say something like, well, there's an example later. And in the unsupervised adaptation, you have no parallel data in the target domain, okay? But you might have, you have the data in your source side, or maybe in your target side, but there are different techniques for these things. But basically, what you could potentially do is you have the features that you have trained, or the feature of your model that you have trained on the general domain, right? And now you have a bunch of new data that come in from a very different domain that you have never seen before. And now what you can try to do is make sure that these, we'll talk about it later, but you want to make sure that these new data that have a very different distributions do not produce very different distributions over your model's outputs or their features. So going back to the supervised domain adaptation, basically one idea that has been applied in many different flavors also recently is on the right side, let's say you have this HT denotes like an LSTM or a layer of the transformer or whatever, and given that you have trained on your inputs and your outputs, and when you get the correct labels for your in-domain, like the new domain, what you can do is maybe, instead of just adapting those parameters, like, just updating them, what you could do is add an additional component that will be domain specific, and you will train that, and then in order to produce your final output, you will use the representations from both the general domain and the specific domain component that you have trained on your parallel data, and this works quite well. Another option that you can do is, another option that you have is to append the domain tag to your input. Let me see if I have it here. So that you learn the model even during training. That the text that you're training now comes from the news domain, and that way you might have you will also learn embeddings for these tags, right? So what you can do is during training, append the domain tags, learn those embeddings, and then use them during inference, during testing, in order to basically bias your model to use to produce outputs that match that tag, right? And there are many interesting things that could happen here. Like, let's say you have trained on just news text and medical text, and these are very, very different. Like, you would all do great in distinguishing those two types of text, given just a few examples. But what if I created, after training on a bunch of these two domains, I just averaged the news domain and the medical domain and created an intermediate medical news domain? Then you can see examples where the model basically outputs something that would match our intuition of medical news domain. Just something to point out. Now, if you do not have a lot of parallel data, or just enough parallel or label data in your new domain that you want to adapt to, one option that you can use is this feature matching, which basically what you want to do is adapt the layers or some layers of your network so that any incoming unlabeled data do not produce very, very different distributions of features from your model. So in this case, you have a big, that's a classification model, and you have a bunch of inputs and an encoder, and then you have trained the top part, the green one, on your labels that you can see, like dark gray. And now, when you have unlabeled data, what you make sure by using this multi-kernel mean maximum discrepancy, which is again just a form of regularization, is basically now what you want to do is whenever you have unlabeled input from presumably a new domain, you make sure that the blue dots, right, the features that you get from these unlabeled data are not very far, or they are not from different distributions than the distribution of the green dots. Okay. Right. Or basically you could. There's another one that uses again this exact same idea using an adversarial network, right? So if you give the adversarial network the green features, the green values, and the blue values, if the adversarial net is able to distinguish those two and figure out if these features were created from labeled or from unlabeled data, or from the old domain and the new domain data, then you haven't done a good job, right? So if the adversarial network is not able to distinguish those two, then basically you've made sure that your network produces similar features even on unseen data. Okay, so now let's talk about multilingual models, which again is just another flavor of multitask learning. In multilingual models, one can have just inputs in many languages for the same task. So let's say you want to train a part-of-speech tagger. Is there a reason that it has to be just an English part-of-speech tagger, or could it be a European languages part-of-speech tagger, or any of those examples? Typically, in these cases, what has been shown to be very useful is to use an adversarial objective over the learned representations of your source in order to encourage the model to produce language invariant representations, right? That means that if you have, let me just show you this here. We have input from both English and from Chinese, right? And we have our encoder, which is green and blue examples. And you can use, like, you have the decoder that does the sentiment classification that you don't care about, but there's an adversarial part here that tries to identify the language of the source, right? And what you do, basically, is you don't want, the adversarial is adversarial because it tries to do the opposite of what you want, so what you do is you reverse the gradient when you do the backpropagation, right? You've seen this before. But the idea is, if the adversarial component is able to distinguish the two languages correctly, it means that you've done a poor job at learning language invariant representations. Okay. Yeah. Yeah, and that thing is very successful in many tasks. In the case of multilingual structured prediction, or when you want multilingual outputs, let's say training a machine translation model to translate both from any language to any language, right? This has been done. Things are harder, but usually there are a bunch of simple methods that can deal with. One of them is provide an embedding that tells your model what your output should be like, right? And this is very similar to the domain embedding that we talked about before. Although there, the domain embedding described also the input, right? In the domain embedding, you had both the inputs and the outputs hopefully be in the same domain. But in this case, in Yulia Tsvetkov's work, they were basically they were trained a multilingual language model, except over phonemes, and all they did is provide a feature vector that was language specific that provide the typological features, and typological features are just features that linguists have created that describe the language, as in, is the language fully native, or is it fusional, or is it something else? Is the language, does it prefer a subject-verb-object word order, or does it prefer an SOV or order? So you just create a feature vector, which are typically zeros and ones, but describe the language, and it would be very rare that you have like languages have the exact same feature vectors either way. And you provided an additional input in order to tell your model what your expected output should look like. In the case of sequence-to-sequence multilingual models, again, the idea of the tag that tells you either what your source distribution is or what your target distribution should be has been very successful. So, for example, in multilingual machine translation, people have been training models on going, for example, from English to both French and Japanese, and by changing, just providing the different tag, the model is able to model this task and provide a Japanese example when it provided the Japanese tag and the French one in the French. And you could also, in other cases, for example, in Google's multilingual system, they provided a source language tag and a target language tag, right? Or it could be like one big tag that is like N to D, N to English to German, or English to Japanese. And this has the potential to allow for zero-shot learning. So for example, you train one model using the same encoder and decoder on both English to French and French to English, and also Japanese to English and English to Japanese, right? Providing the appropriate tags in every case. Now the model has never been trained on French to Japanese or Japanese to French, right? However, if you just provide it during inference time with a French sentence and tell it in the input tag that the input is French, and give it an output tag that's Japanese, then the model will produce a Japanese sentence that looks very much like a translation of what it is. And that's quite effective, but it's not, to be fair, it's not as effective as doing this two-step translation using that model. So translating through English. So you give it the French sentence and you create the English, which is the language that it has actually seen lots of data on, and then you take that English sentence and you translate it into Japanese, and this works better. Right. There's this other option of using like a teacher-student network for multilingual adaptation. And the idea is, exactly like I said, to use a better pivoted model to teach the zero shot model how to translate. So in our previous case, the zero shot model was the French to Japanese. And basically the idea is that you train through the pivoted data that you imagine or hallucinate in order to train your zero shot model. We won't go into more details about this, but the paper is super interesting. Yeah, okay, so in general, there's other types of multitask models that, in general occur. So if you want to do, that was in the structured prediction, run, you might have, the most common is doing pre-training on lots of plain text or translated text, and use these information for syntactic analysis tasks. For example, like, let me give you an example. When you're translating between languages, basically, because the syntax of two languages varies, then presumably, if you train a machine translation task on lots of data, then you also learn to transfer, you learn features that are able to capture syntax exactly because these are needed in order to properly translate, right? So you could use these features to also produce the syntax annotations in the language that you care about. Another thing that you could do is train on multiple annotation tasks. And this might be very useful in the cases where you might have different annotation types that all basically denote the same thing, right? So if you have a tree bank that denotes a tag, like a part of speech tag for nouns, that's just NN. Or if you have a different tree bank that was created 12 years later and decided to denote nouns as noun, right? You could potentially do multitask learning using both of these types of annotations. Although, again, in this stupid example that I gave you, you could just map the two, but you know what I mean. So yeah, you can either train with multiple annotation standards or multiple annotation tasks, because the different tasks, like syntactic parsing is different than dependency parsing, but they both somewhat capture the structure of the language. So what if you use both of them? And one very interesting idea here is that presumably there's a hierarchy in the tasks. So when you do translation, for example, right, there's the simple task of understanding every single word, right? There's the task of understanding sentences. There's the task of understanding syntax, and then there's the task of figuring out the semantics of the source sentence, of like what is the actual meaning. And you could potentially, as we'll see later, use the different tasks to capture this notion of hierarchy. So going first to the multiple annotation standards, it is very, very common that you'll have different annotation standards across different data sets. So one solution is to just train models that adjust to all these different annotation standards for stuff like semantic parsing or possibly syntactic parsing and other things. And what's also interesting is that different annotators might have followed slightly different, within the same annotation standard. People perceive things differently, or they might just be making mistakes. But either way, it is even possible to adapt to the individual annotators, basically taking multitask learning to a very, very, very specialized, where you can think of every task being adapting to the language distribution of the English that I speak, or the English that you speak, or the English that someone else speaks, or the annotations that we have produced. Right, and here's the idea of using different layers for different tasks. And the idea is that more complex tasks are captured from further deep in our network. In this work by Hashimoto and others, basically what they did is they were working, the final task that they care about was textual entailment, where you're given two sentences and you want to say if the first sentence entails the second, or if they're not related, or the third option is that it does not entail, like it's the opposite of the second sentence. And basically, instead of just having like the two encoders of the two sentences producing some representation that is then used for the entailment task, they also train the different layers of these encoders to also produce different annotations. So you have the word level annotations where you do part of speech tagging from, say, the first layer, and then you might also want to do chunking, like splitting into phrases, and then you use some of the next layers to actually train on dependency parsing, because you might have labels for that. And basically, what this does is it makes the model, you encourage or almost like force the model to learn the representations that are also useful for these tasks, because you have the outside knowledge that knowing that having these representations or having features that capture these representations would help you on your downstream task. And the same idea was also used for speech recognition, where again, here the hierarchy is even clearer, right? In the speech recognition community, or the traditional speech recognition, initially you had just the raw sounds, right? And then you assume that these were generated by some GMMs from a specific Gaussian, from a Gaussian mixture model, so from one of the mixtures. And then basically each different sound, each different phoneme had its own different Gaussians. And then all of these work together to create triphones, and then all of those work together to create phones, or sorry, to create long sentences, words and long sentences. So what Supervised did and other things is basically, you encode the raw audio and with LSTMs, and then you have a hierarchy of like 1, 2, 3 layers, but you use the first layer to also add the loss on how well does it do on predicting the state of the GMM that a traditional speech recognition model would use. And the second layer would learn to predict the phones. And the last layer would actually learn to predict the characters that match the transcription. So this is another example of where explicit tell your model, like, this layer should basically learn to do this task that is then useful for the next task that this other layer is doing, and so forth until the final task that you actually care about. So just to summarize, when it comes to multitask learning, there's a bunch of different design dimensions that you can consider when designing your model. So the first one is the order that you will use the tasks. Right? The first thing, like pre-training or transfer, is where you first train on the first task, and then you initialize with all the methods that we talked about before, and then do the next task, the X to Z task. And yeah, BERT or ELMO or any other contextual embeddings fall into this category. Another thing is just train jointly on the two tasks, alternating between the two. Or if you're lucky enough and you have data of triples where you have given a source, you have both outputs for the two tasks, you can just train on both of them at the same time. And when you're doing that, you might end up sharing different layers, as we show in the last examples. And finally, there is a bunch of like different variations where you can even do like multitask learning, effectively only having 2 data sources. So in this prime example for machine translation, what Q and others did is basically the second task is reconstruction of the source. So they had a model that translated X into Y, and then they added another decoder on top that received that Y and attempted to reconstruct the source. And that's again very intuitive, right? In machine translation, if I say something, if I have a sentence in Greek and I translate it in Italian, then if I translate back, I should get the same sentence. So that's another form of supervision that you can give your model, so that you'd encourage this intuition by having a loss from the reconstruction. Another design dimension is what you will do about parameter sharing. So the first thing is just, not share any parameters across the two tasks and tie them in a soft manner. Or you could share some of them and use, in the very typical scenario, and the most common one, just share the encoder, because what you care about is the actual task invariant representations that are good for all the tasks. Or in many cases, you might just using the pre-computed embeddings, which, okay, in the case of Bird and Elmo, these are kind of tied, right? Because if you use the contextual embeddings, then in the case of Elmo, you actually have an encoder over the source. Or you could, share all of the parameters, where either you initialize, or you basically are kind of sharing. And in the case, like in the multilingual or the domain adaptation case that we talked about, you adapt all of the parameters and use a tag for providing the model information about the language, or the task, or basically the source distribution and or the target distribution. And another even more recent thing is you can attempt to have a model that learns which parameters to share across different tasks. And there's this, that paper that I mentioned with sluice networks is not the first one to do it, but it's super interesting. There's other work, especially, and also in machine translation by Reza Hafari and others. But that's another super cool idea, right? Instead of giving our possibly false situations about which tasks might help, or how many of the embeddings or the encoder or the decoder layer should be shared, what if we had our model learn to do it itself? Yeah, that's about it. I guess we're early, but if you guys have any questions, or yeah.
But does this use network no better than previous selection?
Sorry, what?
Like the network you just introduced, the one that learns to share parameters, that perform better than human selections?
Yeah. In that paper, they at least I think in one of the tasks that they one of the downstream tasks that they evaluated on, they were doing better than the predefined sharing.
So I have a follow-up on that, just kind of in general, not specific to sluice networks, but in terms of hyperparameter tuning. So hyperparameter tuning, I think it's very common that you'll be able to do a better job than a machine. So like it's very common that humans are have better intuitions and can come up with like network architectures or ways of sharing things. And then you do a grid search over the things that seem useful to you, and that usually works pretty well. There are black box optimization techniques, like what is called like Bayesian optimization, or also sometimes called meta learning, where you try to learn the hyperparameters on its own. And overall, like I think the impression of a lot of people is that these are kind of disappointing. They sound really cool at first, like they can search for your hyperparameters for you, but it turns out that actually, graduate students and researchers are pretty good at finding optimal hyperparameters, especially if their paper being accepted depends on it. So,
well, but you might also actually have done a very steep graduate ascent on finding, on learning those.
So you do help. I mean, nobody doesn't tune hyperparameters, but just checking the space that you tune over. Humans are actually pretty good at this, and I don't think it's necessarily the case that having a complicated method will outperform that. But that being said, if you have lots of patience, if you have a method that automatically tunes things, and you have lots of patience or lots of machines, then it works.
So the reading talked a bit about like adversarial tasks. Could you like give an example of when you would use an adversarial task rather than a related task?
So a prime example is like when you train a multilingual system to have the adversarial task be predicting the language. That's one example. In the case of domain adaptation, that could be predicting, maybe if you want, I'm not sure if that would help or not, predicting the domain of the source. If you actually want to learn something like domain invariant representations. People have used lots of other adversarial tasks. I'm trying to think of, do you have any? Or?
Well, I think what Antonis mentioned are two good examples, but just to generalize a little bit more, it's very common to use adversarial objectives when you want to try to match two distributions, and one common thing is to try to match two distributions in feature space over two tasks where you want them to share more information between them. So that includes training on multiple languages or training on multiple domains. That being said, there are times when adversarial objectives are not a good thing, and I mentioned this when we were talking about the adversarial thing before, but like, if you train an adversarial objective to try to prevent distinguishing between two types of data, if that information about the type of data is really important to solving the final task, then that can actually hurt performance significantly. So an example is, if everybody hates apartments, but everybody loves movies, and then you do an adversarial objective over apartment reviews and movie reviews, then you'll lose the distributional information about like how, for sentiment analysis, for example, about like whether you expect lots of good things for, bad things for apartments and good things for movies.
Okay. I'll just